Okay, everybody, I'm on page 86 of your unit packet, and this pre-work is for our Wednesday lunch tutorial on differential equations. So if you have a mandatory lunch tutorial tomorrow and Wednesday, you need to have your packet out onto page 86 and take notes for me here. The first thing we're going to do in tutorials tomorrow is check your notes and check the additional problems that you need to do as pre-work on the following page. So make sure you have your packet out and you're ready because this is part of your grade. Okay, so in this problem, you've got a landfill that contained 1,400 tons of solid waste back in 2010. The increasing function W models the total amount of solid waste stored in that landfill. Planners estimate that W will satisfy this differential equation for 20 years. W is in tons and time is in years from the start of 2010. So in this first part, we're asked to find the particular solution to our differential equation given this initial condition 0, 1,400. Pretty standard problem here. And we know based on what we just studied in our last unit that if I want to find a particular solution, I'm solving the differential equation by way of separating and integrating. Separate and integrate. So the first thing we always do in this kind of thing is get rid of dt. That allows us to be looking at an equation that's almost ready for the integrating piece, but I can't do that integration until I move the w minus 30 over to the other side. So a great way to record that is 1 over w minus 30 dw equals 1/25 dt. After that algebraic manipulation, separating's done, I'm ready to integrate. So I have to just think to myself what functions came before these here sitting inside the integral. 1 over w minus 30 is a reciprocal function. The only place that could have come from is a log because of our log derivative rules. And 1/25 had to have come from a 1/25 t plus c, of course. So I start to identify ways to isolate w. First thing I'll do is put an e on both sides in order to cancel. I get w minus 30 equals to, let's not forget, big C e to the 1/25 t. I want to drop those absolute value bars and move the 30 to the other side. So in order to do that, I've got to consider the plus or minus solution set here. And because I've got a positive 1,400, I'm going to choose the positive. Move that 30 over at the same time, and I get 30 plus big C e to the 1/25 t as my general solution. And the only thing required of me now is to go find the particular. So I'll put 1,400 in for w, and I'll put the 0 in for t in just a second. C e to the 1/25 times 0 up top. Do a little bit of mental math, and I get 1,400 equals 30 plus, well, 1/25 times 0 is 0. E to the 0 is 1, c times 1 is c. So it looks like my c value is 1,100. And that means that my final answer, my particular solution, is w equals 30 plus 1,100 e to the 1/25 t. Separated, integrated, and done. A pretty standard follow-up is here in part A, where we're required to use the line tangent to the graph of w at t equals 0 to approximate a given value. So line tangent to a graph means y equals m times x minus x1 plus y1. And the two things I need are a point and a slope. The only part that I've been given here is that the point is going to have a 0 as our input. I need to go investigate and try and find the output and the slope. So that's not too bad here because at the beginning of the problem I was told that at 0 there are already 1,400 tons of waste in the landfill. So there's my point of tangency. And a slope I know is a derivative, which shouldn't be too difficult because they gave me that derivative, if I'm remembering correctly. dw dt is 1/25 W minus 300. So if I want my slope at this point of tangency, I just need to use my derivative formula to identify that slope value. So dw dt is going to equal 1 over 25 times my current tons of waste, 1,400, minus 300. A little bit of math, that's 1 over 25 times 1,100. And, oh dear, 1,100 over 125. I may or not be cheating right now using the calculator on my cell phone. I got 44 for that division. So my tangent line equation with a slope of 44 is y equals 44. I'm going to put a t here, minus 0 plus 1,400. And I want to use that tangent line to approximate the amount of solid waste in the landfill at t equals 1/4. So that means W of 1/4 is approximately equal to 44 times 1/4 minus 0 plus 1,400. Tangent line, done. Our next follow-up here asks us to find the double derivative in terms of W and use that double derivative to determine whether our answer that we just came up with for our tangent line approximation over or underestimates the actual value. So again, let's not forget what we already know to be true. The first derivative of this function is 1 over 25 times W minus 300. Or if these parentheses bother you, how about 1 over 25W minus 12? I promise 1/25 of 300 is 12. That's my first derivative. So if I want to find the double here, what I need to do is take the derivative of 1 over 25W minus 12. Well, the derivative of 1 over 25W is 1 over 25 times W prime, and the derivative of 12 is 0. So my double derivative is 1/25 W prime. Another way of saying that is dW dt. And it does say back here what I highlighted in terms of W. So a nice fix here at the very end in order to get full credit is to just take dW dt back out of the problem and plug in what we know dW dt is. And here's my double derivative in terms of W. Now, is this an overestimate or an underestimate? Well, this is my double derivative. What I'm seeing here is that if I were to consider what happens when I have actual waste in my landfill, maybe 1,400 tons of waste or something like that. 1,400 minus 300 we saw earlier is 1,100. And I'm taking that and multiplying by 1/25 and multiplying by 1/25 again. I'm getting a positive double derivative here, which indicates that my curve is concave up. If I draw a tangent line on a concave up curve, I can see that it's always underneath the graph in blue, generating an underestimate. We were also told at the very beginning of the problem that W is an increasing function. So if the function's waste is always growing and growing and growing, if I started with 1,400 tons of waste and that number is only getting bigger, this double derivative is never going to be negative. It's always going to be positive because there's no value of W I could plug in that would generate a number less than 0 when I subtracted 300. So since W is increasing, I'm going to say always increasing. This double derivative is always positive. Therefore, W is concave up, and we have an underestimate. That conclusion cannot be made unless we discuss the concavity of the original curve. So, another follow-up here, very common one, in fact, utilizing all of these big ideas. All right, and finally here, the last extension asks us to find a limit. We haven't had to do limits in forever, and this is an infinite limit. And try and discuss what's going on with our landfill here. So if you remember back at the very beginning when I separated and integrated, I think I got an equation for myself that said W equals 30 plus 1100 e to the 125th t. That's a t up there. And what I want to try and do is find the limit as t approaches infinity of this function. 30 plus 1100 e to the 125th t. So what I'm really drawn to here is this exponential. That's where the variable is. I want to know what happens to that function as t gets larger and larger and larger. So there's a way to do this analytically. Plug in a big number, take 1/25th of that big number, put it on an e, multiply by 1100 and add 30. I always try to tell you to do this visually. E to the 125th t, that power is positive up there, so this is a growth function. And as t's get bigger and bigger and bigger and bigger over here, you can see that our function just goes up and up and up, higher up on the y-axis. So that exponential function approaches infinity as t's get larger. So what I've got here is 30 plus 1100 of a very, I'm going to put this in quotations, like large value. If I take a really large value, multiply by 1100 and add 30, I think I still get something really, really big. So my limit as time goes on is infinite. Interpret the meaning of my answer. That means that that waste in the landfill is growing infinitely, and it's going to be bigger and bigger and bigger as time goes on. I don't know if that's the most realistic approach here. Can a landfill actually store an infinite amount of waste? But according to this differential equation in this model, that's what the mathematics tells us. All right, so we're done with our model problems. You've got some other pre-work to take care of. We're going to be scoring that in class tomorrow, and that'll be part of your grade. So get busy and good luck.